Let's talk about Green's theorem. So Green's theorem is our first of three major theorems in vector calculus. So the context here is that we are studying domains in two dimensions. So throughout this lecture, D will denote a domain in R2. So perhaps the domain looks like some blob like this. So the first thing we need to understand is the relationship between this domain and its boundary curve. So by definition, the boundary of a domain is denoted by partial d. This partial has no calculus significance. It's simply notation used to refer to this concept. So the boundary is denoted by partial d. And what this refers to is the outer edge of the domain. So in this picture here, we're looking at a two-dimensional domain, and the boundary refers to the outer edge of this domain. So while the domain itself is two-dimensional, the boundary is a one-dimensional curve. And so we need some vocabulary at our disposal to understand boundary curves. So the definition that we need to understand next is the notion of a simple closed curve. A simple closed curve is a non-self-intersecting loop. So to study a simple closed curve, we need two things. We need the curve to start and end at the same point, and we need that curve to do so in such a way that it doesn't intersect itself. So here we have four different examples of curves, and I want to go through each one and test whether or not the curve is simple and whether or not the curve is closed. In this first example on the left, we have a curve that maybe starts at the top here and then sort of loops around and then intersects itself at this point and then ends at the bottom. Because this curve intersects itself, this curve is considered to be not simple. On the other hand, we can see here that the curve sort of starts and ends at different places. So this curve is also not closed. So in the example on the left here, our curve is not simple because it intersects itself once, and it's not closed because it starts and ends at different positions. If we move to the second example from the left here, we see we're studying this sort of spiral curve. So maybe we start in the middle and then we sort of spiral out as depicted. This curve is simple, and it's simple because it never intersects itself. However, this curve is not closed because the start point is different from the end point. So here we have an example of a curve that is simple, but it is not closed. In this third example, we're studying sort of like this figure 8 pattern, or maybe we could view this as maybe an infinity sign. No matter where we choose the start point, we can imagine sort of maybe motion along the curve. And the curve definitely starts and ends at the same position, which means that this is a closed curve. However, there is one point of intersection on the curve, and that's right in the center here. So this is an example of a curve that is not simple because there is an intersection. In our last example, we see that no matter what point we choose, if we travel around the curve, we start and end at the same position, and there are also no other points of self-intersection. So the fact that there are no points of intersection here indicates that this curve is simple, and the fact that the start point is guaranteed to be the end point means that this curve is closed. So it's curves that look like this last example that we are going to be most interested in. Now, when our curve is closed, we use special notation to refer to a line integral over the curve. So the symbol integral over a curve C with a circle in the middle indicates that C consists of one or more closed curves. So whenever we see a circle in an integral, what that means is that we're taking a line integral over a closed curve, but there is no new calculus. So the circle is only meant to indicate that the curve in play consists of one or more closed curves. We'll see many examples of this notation later in this lecture. Okay, so our convention is to work with domains D for which the boundary curve, partial D, is the union of simple closed curves. So what this means is that we're going to be studying domains that in general look maybe something like this. Here we have a figure representing a two-dimensional domain, and this two-dimensional domain happens to have two sort of holes in it. So what does the boundary look like here? Well, there's sort of three parts to the boundary. There's this outer edge, and then there are these two inner edges. When our domain looks something like this, what we say is that the boundary is the union of these three simple closed curves. So here we write boundary of D equals C1 union C2 union C3. So this sort of U symbol means union. What we're doing is we're looking at all three of these curves together to produce the boundary of this two-dimensional region. So the next thing we need to understand is the notion of orientation. Previously, when we've worked with curves, we have parametrized our curves in such a way that we establish a direction of motion which is given by the unit tangent vector. So the idea here is that the location of our domain relative to the unit tangent vector of the boundary curve determines the orientation of the boundary curve. So we have two archetypes in this figure here. So here we have the same domain, but one thing to notice is that on the left, we have oriented the domain in such a way that the domain is parametrized in a way that it's traveling counterclockwise outside of this region. And on the right, we've parametrized our boundary curve in such a way that the direction of travel is clockwise outside of the region. So the idea here is that if we choose any point on the boundary, so here we're choosing this point sort of in the upper left-hand region of this boundary, we can look at the unit tangent vector, and because our parametrization of this boundary curve is traveling counterclockwise along the outside of the domain, we can imagine ourselves standing at this point and looking in the direction of the unit tangent vector. Well, when we look in that direction, we see that the domain itself is to the left of the region, or is to the left of the unit tangent vector, and we see that the domain is not to the right of the unit tangent. When our figure looks like this, so meaning that the domain is to the left of the unit tangent vector, we say that the boundary curve is positively oriented. So when we stand at a point and look in the direction of the unit tangent vector, and the domain is to the left of the region, not to the right of the region, we say that the boundary curve is positively oriented. In our second prototype, or our second archetype on the right here, what we see is an example where if we stood at a point and looked in the direction of the unit tangent vector, we would see that the domain is actually to the right of the region, not to the left of to the right of the unit tangent vector, not to the left of the unit tangent vector. What this means is that the boundary curve, or the boundary of our domain, is negatively oriented. So positively oriented means that the domain is to the left of the unit tangent vector, and negatively oriented means that the domain is to the right of the unit tangent vector. So let's do an example here to make sure we understand this concept. So one thing to point out is that in general, our domain might not look something like our examples in this introduction here. Perhaps our domain has holes in it. So we have to look at each part of the boundary of our domain in order to establish orientation. So on the left here, we're looking at an example where our domain consists of three boundary curves. There's an outer edge, and then there's these two inner parts. Well, if we look at the outer edge, we see that we're traveling counterclockwise outside of the region. And if we were to look at any point and then look down the unit tangent vector, we would see that the domain is to the left of the unit tangent vector. On the other hand, if we were looking at any one of these two boundary curves on the inside of the domain, we would see that if we focused on one point and looked in the direction of the unit tangent vector, the domain is still to the left of the unit tangent vector, not to the right. So that happens in both parts of the inside of this domain. So this indicates that the boundary of this domain is positively oriented. On the right over here, you'll notice that all of the directions are switched. On the outer edge, we are traveling clockwise around the region, and on the inner edges, we're traveling counterclockwise inside of the region. If we look at the outer edge here and focus on a point and look in the direction of the unit tangent vector, we would find that the domain is to the right of the unit tangent, not to the left. And if we look at either part of the inner boundary curves and focused on a point, we would find that the domain is to the right of the unit tangent vector, not to the left. This indicates that our orientation on the right is the negative orientation, whereas on the left, our orientation was the positive orientation, because the domain is always to the left of the unit tangent vector. So the convention that we will always assume whenever we're discussing two-dimensional domains is that the boundary curve is positively oriented. So whenever we are studying a two-dimensional domain, we will always assume that the boundary of that domain has the positive orientation. So this allows us to do what's called, I like to call at least, boundary curve arithmetic. So if we assume that the boundary curve has positive orientation, we can look at each part of the boundary of our domain and figure out whether or not it's positively weighted or negatively weighted. Let's see this with an example. So here we have a two-dimensional domain, and suppose that we have managed to parameterize each part of the three, or each of the three parts of the boundary here. Well, if we look at the outer edge here, maybe we call this C1. What we find is that on the outside, we're traveling clockwise throughout the region. And if we look at any point and then look down the unit tangent vector, we would find that the region is actually to the right of the unit tangent, not to the left. So what this indicates is that C1 is actually working against the positive orientation. If we look at this curve, inner curve to the left here, we find that we're traveling in the clockwise direction. And if we look at any point on that curve and look down the unit tangent, we would find the domain to be to the right again, which means that C2 is giving us the negative orientation. And if we look at this last boundary curve, C3, we can focus on any point and look in the direction of the unit tangent, and we would find that the domain is to the left of the unit tangent. So this indicates that C3 is respecting positive orientation, whereas C1 and C2 respect negative orientation. So if we assume that the region is supposed to have the positive orientation, the way we would indicate this, given these particular parameterizations, is we would say that the boundary of this domain is negative C1, because C1 had the negative orientation. Then we would subtract C2 to indicate that C2 had the negative orientation. And then we would add C3 because C3 had the positive orientation. So this notation is meant to tell us that C1 and C2 were parameterized in the opposite direction of the positive orientation. And then when we add C3, this is meant to indicate that C3 was parameterized in such a way to respect positive orientation. Okay, so the last thing we should understand about boundaries is what line integrals are meant to represent over boundaries. So let's recall a concept from from maybe a little over a month ago, which is the notion of a vector line integral of a vector field over a parametrized curve. The notation we introduced to refer to a vector line integral of a vector field is the integral over the parametrization of a curve of the dot product of the vector field with this symbol d bold s. And what this line integral was meant to represent was the integral over the domain of the parameterization of the vector field with the parameterization plugged in, dotted with the velocity of the parameterization dt. And the purpose of studying vector line integrals is to calculate the work done by a vector field over a parameterized curve. So vector line integrals calculate work. The context that we will now be interested in is the situation where we are studying some two-dimensional domain, which is represented in blue here, over which a vector field is defined. All of these arrows in green are meant to represent some vector field represented by f. So the context for us is we are studying a two-dimensional domain where there is a vector field defined. The problem we will now turn our attention to is the problem of figuring out the work done by this vector field over the boundary curve of this domain. And this work problem has a special name. This is called the circulation of the vector field around the domain. So by definition, the circulation of a vector field around a two-dimensional domain is the work integral, which is the line integral over the boundary curve of the domain of the vector field dotted with the symbol d bold s. And notice again that here we're using the symbol integral with the circle in the middle. Again, this circle in the middle is only meant to signify that the boundary curve of this domain consists of one or more closed curves. And one thing to point out here is that if we assume that our domain has the positive orientation, then the circulation integrals respect boundary arithmetic. So if we go back to our example where our two-dimensional domain had three different boundary curves, so it had its outer boundary curve and its two inner boundary curves, this is exactly the example we saw a few slides ago, where the outer boundary curve C1 and this inner boundary curve C2 actually respected the negative orientation, and then this boundary curve C3 respected the positive orientation. What we find is that the circulation integral, which is the integral of the vector field dotted with d vector s around the boundary of this region, can actually break apart as three different integrals. So here we're taking the integral of f dotted with d vector s around the curve C1, but we're multiplying that integral by -1 because C1 had the negative orientation. Then we subtract the work integral of f dot d vector s along C2, and we subtract because C2 had the negative orientation. Finally, we add the work integral f dot d vector s along C3 because C3 had the positive orientation. So if we understand orientations, we can calculate a circulation problem by breaking it apart as several circulation problems along the different parts of these boundary curves. But we have to multiply by plus or minus 1, depending on whether or not our parameterization respected the positive orientation. So let's look at an example of calculating circulation. Here, we're defining a domain in 2 dimensions to be defined by the inequalities 1 is less than or equal to x squared plus y squared is less than or equal to 2. So this should actually say 4. So this 2 should be a 4. I will fix that. So here we're looking at 1 is less than or equal to x squared plus y squared is less than or equal to 4. And we're defining a vector field on R2 given by coordinates 1, x. And here our vector field is given the units of newtons. So our visual representation of this domain consists of an inner circle with radius 1 and an outer circle with radius 2. So again, this 2 should be a 4, which would indicate that the radius would be 2. So our region has an outer boundary curve, which is represented by the circle of radius 2, and then there's an inner boundary curve, which is represented by the circle of radius 1. Again, we always assume that our domain has boundary endowed with the positive orientation. So what we find here is that to have positive orientation, our outer circle with radius 2 must travel along the region in a counterclockwise manner, so that the domain is to the left of the unit tangent, and then we need this inner part of the boundary curve to travel clockwise inside of the region, so that the domain is again to the left of the unit tangent vector. So we can look at how our boundary curves ought to be parameterized. I'm going to call a parameterization of this outer boundary curve x sub outer of t. And what we need to do here is we need to parameterize the circle of radius 2 in such a way that the direction of motion is counterclockwise. All we need to do here is take the parameterization for the unit circle, which is cosine t comma sine t, and multiply by 2. We also want to parameterize the inner boundary curve, which I'm going to call x sub inner. And we need to parameterize this inner boundary curve in such a way that the direction of motion is clockwise. So all we need to do here is parameterize the unit circle in such a way that the direction is counterclockwise, in such a way that the direction is clockwise. So here, x sub inner of t should be cosine comma sine, but normally cosine comma sine gives us counterclockwise motion. So I'm replacing the t here with negative t so that we can respect the positive orientation of the domain. So now, if we were to calculate the circulation integral along x sub outer of f dot ds, this would be an ordinary work integral. To calculate this integral, we take the dot product of the force vector, where we replace our x in the force vector with x coming from the parameterization of x sub outer here. So this x gets replaced by 2 times cosine t. And then we dot with the velocity vector of this part of the parameterization. Here, the parameterization is from 0 to 2 pi. And when we take the dot product and do the calculus, we end up getting 4 pi. And the units here should be Newton meters. If we were to calculate the work integral along x sub inner here, the mechanics are the same, but the ingredients are different. Again, we're taking the force vector and dotting with velocity, but here we're replacing the x in the force vector with the x coordinate of our parameterization, which is cosine of negative t. Then we dot with the velocity vector for x sub inner, which is sine of negative t, negative cosine of negative t. When we take our dot product here and do the calculus, we end up with negative pi Newton meters. So I encourage you to go through and complete the calculus here just for practice. But the question now is, what do we do with these results? Well, we can now use these results to calculate the circulation of our vector field around the domain. By definition, this is the vector line integral of f along the boundary of this domain. And again, the circle here is simply meant to signify that the domain consists of, in this case, 2 closed curves. And since here we have 2 different parts of the boundary that we've parameterized with the correct orientation, what we need to do is we need to add these 2 vector line integrals. We want to take the work done on the outer boundary and add it to the work done on the inner boundary. So in this case, we want to take 4 pi Newton meters and subtract pi Newton meters, which ends up being 3 pi Newton meters. So the circulation of a vector field around a domain is by definition the work done by the vector field along the boundary of the domain. And in this problem, the boundary of our domain consists of 2 different regions, or 2 different curves. So we calculate the work done on both of these curves with the correct orientations, and then we add the 2 results. So circulation equals work done by the vector field on the boundary of the two-dimensional domain.